Coffee? Oh no, 1 o'clock, right?
At 1 o'clock.
Okay.
1:30. Just not gonna be
You go for a run, go for a nap, or sit in a lecture. And the last two are equivalent, unfortunately. So, this is the worst board in the world. Okay. So in that first question, you get to a beta function, which is pretty awesome. So, but basically, it's, if I have it right, right?
Also, is it a B or a beta?
Well, capital beta is a B.
Okay.
The Greeks had that whole alpha beta thing going, right? That's it. That's an interesting. So Glick in his information book, there was a piece in there where he talks about the alphabet and how it was invented really only once in the Middle East, basically, and then it was sort of emulated, but it was contagious. There's a really nice line. The alphabet was contagious. Right, so now you had atoms and words and molecules. Fantastic. All right. So this thing, so you can use, so once you've got to this, you're going to have blobs in here, right? So there'll be apples in here and, I don't know, some exploit, like a leaf. Oh, a leaf. That's a good one. And then maybe a campfire. Something, right? There are different things in here, okay? It's good not to use X's and Y's because we have this silly thing about X's and Y's. So fruit calculus involves fruit. It's really good. Writing on the board is so much fun. All right, so let's see. So gamma of X, the Stirling approximation, is this X, the X plus a half. So this thing is growing ridiculously, but then it also has this. It's a very strange looking beast, right? It's tamping it down. So you can, if we say Y is fixed, wow, this is terrible. Y is fixed. I should bring colored chalk in. Y is fixed, X approaching infinity. Then this guy is just stuck, and we have to think about these two. And you're going, right as I said, you're going to have some blobs in there, but basically, if you understand this piece, you can get, yes, you can look up Wikipedia or ask Mr. Wolfram what he thinks, but never ask Mr. Wolfram a question. What's that?
Well, the fact of the matter is that y is this fraction of things where the denominator can be as close to 0 as you like. So the whole fraction can be as large as you like.
Okay, yeah, but it's still fixed, right? It involves rows. It involves the innovation rate. So this is just we're going to think of this one as a constant. So this is a symmetric thing. Just think about the beta function in general. If this is fixed,
Yes.
or this is fixed, and let one of them go to infinity, you have same thing. Yeah. So you have to put this guy into here. Gamma of y stays the same, right? So you'd have this root 2 pi x to x plus a half e to the minus x. That's a square root. Gamma of y. Right, so that's this guy. And then on the bottom, you have root 2 pi. Wow, this place was refurbished too, right? It's unbelievable. Okay, so x plus y.
You usually just save money by getting the cheapest black board like that.
So it's a new board, but it's just,
I mean, maybe it's an old one, but
yeah, from 1922. Wow. Okay. They're watching, of course. So gamma x plus y to the half, plus a half. That's this bit. E to the minus x plus y. Yeah, this guy's in a control room with coffee, right? A Joss Whedon movie. No, we don't want that. Okay, so these guys are going to cancel, and some other things are going to happen, right? This is the tricky bit in here. Yet again, this is one of these guys, 1 plus apple over n to the n. Limit as n approaches infinity. You want to turn it into this. That's a 1, right? So you want to make it a 1 plus something divided by n to the n. This could be 2n, as long as these things are the same, whatever you get there. So we've solved this a little bit. I'll make it into a video thing. What is it? E to the apple. Good. Right. Which is fun. Actually, this is, right, so it's just a side note. Exponentials are pretty awesome, right, because you define them in terms of the, so you have to have whatever the identity is in terms of apples, and then you have plus, this is a terrible board, plus a half, apple squared, plus, right? So matrices work like that, right? So square matrices. really fantastic. So it's all okay. All right. So you're going to have to contend with it. You see, you can pull an x out here, and you'll have 1 plus y over x.
Yes, yeah.
Right? And the y over x, y is fixed. That 1 over x is exactly this, right? So y, x. And then there'll be some power here. So you're going to get some e's, right? And it might help you, might get rid of this guy. There's an e to the minus x here and e to the minus x here. There'll be another e here. Gamma of y is just a number. Y is fixed, right? Y is 7. Think of y as 7. Or 17. That's a good, 73, good random number. 73. Oh, absolutely. So what's the most, I mean, I've blown it, but what's the most random number between 1 and 20? This is a great problem.
17.
Yeah. So you can actually ask people this, and they'll do the right thing, because it's about how little understanding we have of randomness, right? In my chaos course that I took in like 24, Melbourne Uni, which was a great course, this was one of the highlights for sure. So it can't be 1 or 20, right? Because they're at the ends, yeah? Multiples of 5 are right out. Can't be even numbers, because they're not random, obviously. It can't be 3 and multiples of 3 are out 2. That's just too simple. 19 is too close to 20. 13 and 7 are lucky numbers, and 11 is 2 1s. It doesn't look very random. So, and if you ask people, which I've done in classes, the largest number of people will say, you know, you'll get some smart people say it's 2 or 1 or 20 or whatever. Very good. But what's the most random number? And people are like, oh, 17. Would you like to come to Las Vegas? I have some games I want you to play. Human. All right, none of us understand probability. Even when you think about it a lot, it doesn't help. Might make it worse. Okay, so I had a few things to show you. Well, that was one thing. Does that make you happier, sir?
Yeah.
Oh, only a little bit. All right, okay. We can talk some more, all right? There's an advance.
I was just really struggling with the fact that fraction, that the y thing could be as large as I want it to be.
Yeah, it's fine. It's just a constant. This could be 50 bazillions, right?
For random.
It's just a number.
And I can make it as close to
Mm-hmm.
1 as I want.
Mm-hmm. But it's fixed. You fixed it at the start.
That's true.
It's a good point. But you fixed it at the start. Yep. So I've made some silly things like this. Hopefully this should work. Of course, it's not going to work. Yeah. So now there are assignment hints embedded in the videos. And now there are 3 types of assignments, right? There's going to be the one with the solutions. This is just some ridiculous postscript. There's one that just has a link, because if you want to print it out, and then there's one that plays the. So you know, if you open it up, you can play you.
Okay, so we're going to talk about solving
There's a Dalek.
assignments model, and we'll think
Right?
about
So there you go.
difference equations.
So I'll try to improve on those. Obviously,
um,
the lighting over
general.
my
So
kitchen
this
table
is-
isn't so great. But there you go.
so this
The lighting in this room is
It's really good.
No, my head was in the way. What's that?
I was gonna say, he's right, it's good, like, when you play it on your own computer.
Yeah, it's just the lighting in this room.
Oh yeah, and the resolution on this is horrible. Yeah, that's 1080. I mean, it's high def. Yeah.
Where is the embedded version?
So it's just on the website. No?
No, it's there.
We need to refresh.
And also, viewing the non-printer version in Chrome didn't show the video, but you could follow the link.
Right.
That's
So
right. So there's the normal assignment. There's a print version, right? And then this guy here. Yeah. So this one should have one. Oh, it might not work in Chrome. I have no idea what happens in Chrome. So I'm sorry. You have to figure out which thing you have will allow it to happen. Maybe in Safari you run Adobe. You can yeah, but this is not. Yeah. I mean, it's sort of back in the age of when video first appeared. It was horrific, right? Nothing would work, and anyway. Now YouTube is pretty good, and it is on YouTube. So if you get the link, you're good. That's true. So if you click on that, you go to the YouTube thing. Okay. All right. So there's a product enhancement for you guys. I was going to see what this guy's up to. He's a bit of a hero of the show. So this is my wife, actually, Amy Peakey. gets tweeted back and forth. There's some interaction with the Dalek, who has threatened to exterminate her at some later point. This is about what they asked what Daleks eat. There you go, some radiation downstream of Vernon. And of course, there's I do not wear pants. There you go. It's hard to feel cold when one has the warmth of humans attempting to maim each other on TV in the name of sport. Dalek win. Anyway, high quality. Pretty good quality Dalek action. Sorry. Okay. Okay, so that's good. And then I think, so assignments, Mandelbrots, almond bread. Okay. And I've embedded those things, like the very important things like the Highlander trailer. There was a motion towards Mad Max 3, 2 men enter, 1 man leaves, so we might add that. And so we're going to talk about this. We're going to talk about this work of Mandelbrot. We'll sort of finish up with who possibly sort of wins in this little amusing fight. And then I want to talk about a thing called Benford's Law. It's just a tiny little piece, but it's kind of a funny thing that's floating around that helps you catch tax evasion and people cheating in voting and all sorts of things. Possibly. NSA is probably all over this one. It's a bit of a big deal for them. Then I'm going to go back to the overview, and I'm going to get back to some pieces in there. There's a little bit of emergence. There's self-organization, just a tiny bit, and then stat mech. I want to talk about stat mech. Just to touch on that, right? If you're in physics, you would absorb a ton of it, but we're going to see a little bit of it so we have a handle on the next piece, which is robustness. So this is kind of Achilles heel type stories, right? Pretty good most of the time, robust, but fragile. And I'm not really sure why Achilles couldn't have just like double dipped, right? But someone was watching. Now that we think about it, yeah. Well, maybe they just, yeah. Yeah, well,
His mother was drowning him, and then his father dragged him out.
See, it is complicated. It is complicated, yeah. But it's all about process, right? So,
He would have been invincible had his father, had there been some parental communication over, the vulnerability of the child.
Okay, Greek myths with some parent stuff. That's good, yeah.
That's like every.
Greek myths are fantastic, absolutely fantastic. Right, yeah, usually very bad ones. Okay, so we got to this madness here, right? So this is a little exercise for you guys to enjoy. Minimize this horrific function, which is really all about the cost of sending messages versus per informational unit. So you want to minimize that, subject to the constraint that your probabilities of your symbols add up to 1. So that's all fine. So we went through this a little bit. We found out that, well, there's a claim that we get a power law out of it. We're very happy about that. We have to do some magic to figure out what the exponent is. And we talked about it being a bit too high, essentially, and sort of the tunability of this thing is limited, whereas Simon's model has this very nice measurable quantity, which is innovation rate. You can simply measure it, right? That's a fraction of, say, for a book, even though it doesn't model how books are produced, you can simply measure the number of new words, or the number of unique words, right, and get your innovation rate. Easy. And Simon did that, and it matched up quite well, surprisingly well. But here the parameter that's a bit funny is adding what the cost of a space is. Bit strange. All right, so we ended up with this. We said, well, optimization is clearly a huge dominant process in natural systems and human systems and so on. It's a big piece, but there are lots of things fighting against sort of pure optimization. Certainly, one piece we'll come to later on is uncertainty in the environment, very natural piece. So how do you even kind of quantify that or try to address that? We've done some work on that. I'll show you some work, the so-called highly optimized tolerance model. It's really quite nice stuff. All right, so there are some problems with it. It doesn't zoom out to other kinds of areas, like the number of, naturally, right? This is very much about language. So the number of species per genera, that sort of thing, wealth distributions, so on. Okay. So this is a random interlude. So this is a
Under
neural
my
reboot.
tutelage, you will grow
Sound.
from boys into men, from men into gladiators,
I gotta play this again.
and from gladiators into...
So the plan is, I'm going to have these neural reboots, which will be positioned in times of pain so that you guys can feel better about things. This has got nothing to do with anything, but it's funny. It's a good show.
Under my tutelage, you will grow from boys into men, from men into gladiators, and from gladiators into Swansons. Behold, the Swanson Pyramid of Greatness. I've been developing the Swanson Pyramid of Greatness for years. It's a perfectly calibrated recipe for maximum personal achievement. Categories include teamwork, very important. Equally important, selfishness. Take what's yours. America, the only country that matters. If you want to experience other cultures, use an atlas or a ham radio. Cursing, there's only one bad word. Texas. Haircuts, there are 3 acceptable haircuts. High and tight, crew cut, buzz cut. Are the scissors broken in your house, son? Animal proteins, 4 to 8 servings daily. Cow, pig, chicken, deer. Fish, for sport only. Fish meat is practically a vegetable. Friends, 1 to 3 is sufficient. Capitalism, God's way of determining who is smart and who is poor. Skim milk.
Avoid it, sir.
Physical fitness, honor, facial hair, living in the woods, rage, poise, property right, crying, BO, cabins, skim milk. That's right, it's on here twice. Avoid it. Masonry, stillness, torso, intensity, old wooden sailing ships. They're beautiful.
Okay, sorry. But now and then I'm going to have some of these things.
Is that an extended cut? Did it make it to the episode?
I don't know. You're right. You're right. It is? It was in the whole thing? Yeah. I'm sure they cut it down. That was high quality. Anyway, okay. So back to the normal thing. So I just want to I figured out how to put video in PDF, so I'm just... so you can see what's going to go wrong. All right. Really a great advance for this season. So all right, so this is at the end. So Mandelbrot's piece is it's part of a book, right? So it's a chapter in a book. It's not a journal publication. So there are 2 people who reply to him, and so there's this one, A.S.C. Russ. Mandelbrot states that the actual direction of evolution, right, is in fact towards fuller and fuller utilization of places. We are in fact completely without evidence as to the existence of any direction of evolution. I mean, this is amazing to me. This is amazing. It is 1950. Without evidence as to the existence of any direction of evolution in language. And it is axiomatic, which is a bit of a leap, that we shall remain so. Many philologists would deny that a direction of evolution could be theoretically possible. Craziness. Thus, I myself take the view that a language develops in what is essentially a purely random manner. It's just unbelievable. I mean, the structure in the world and language is, Anyway, so I'm not letting this character get away with it. So Mandelbrot it's actually not quite so bad. But I don't know who was posting this, but I'm just putting it. It's just there's a lot of terrible thinking in the world. A lot of it is in my head. I've noticed over the years, and but there is terrible thinking all over the place, and it's just it's not easy to figure things out. That's this. The way we present math, so I've talked about this over and over again, is like here is the nice little path that you should take, right? And many monks died finding that path. All right. So anyway. But it's good to see these are the paths that went wrong. That's a really, we'll see some really beautiful stuff from recent analysis of language that shows some quite striking features. I mean, it is a messy thing, but there's a lot of order as well. As to the fundamental units being the least possible differences between pairs of utterances, this is a logical consequence of the fact that 2 is the least integer greater than 1. Sorry. So, he's a little rude. All right. But just remarkable. I was just reading and thinking, wow, no, axiomatic. Okay. Okay. So, and certainly by that time, I mean, you could see, Old English into Middle English into New, right? There's just a lot of stuff was jettisoned. There's a lot of changing and evolution. I mean, right, okay. So, there's a bit of both obviously going on. So there's been some attempts to do this. So optimization and randomness, you obviously have some balance of these things. We'll talk about highly optimized tolerance, as I said, soon. So this is Gene Carlson, who's at Santa Barbara, and John Doyle is at Caltech. Lots of other papers, there's just a couple. Soleil, a number of nice pieces. So This is Zipf's principle of least effort, fitting into the book. I think I have. I mean, there are still debates in the last few years. I mean, this is just going on and on and on, right? Raisa de Souza, who actually I graduated at MIT, were standing next to each other because Dodds and de Souza. She has a piece when she was at Microsoft, I think. She's at Davis. Kind of connecting all these things together. It's PNAS, it's another piece. Just there's a ton of stuff in there. So here's an interesting piece in the history of all this, right? So Zipf's book was 49. And so there's this fellow, George Miller, who published a number of things. And so there was this story that came out that, basically is just a result of random typing. You would get the same thing. And so there's a paper by the same two guys, Soleil, maybe sort of their colleagues, that basically is titled, "No, Zipf's law is not the result of random monkeys randomly typing." This is like a year ago. So Miller was a colleague of Zipf, as I understand. He was at Harvard as well. And he actually writes the preface to one of his, a reprint of this one of his books, Psychobiology of Language. Anyway, we can, it's kind of rough. We don't have to do this. He does mention genes of language, which is quite interesting. Let me see if I can get that to work. There you go. Random texts do not exhibit the real Zipf's law-like distribution. So can I get this to work? I'm not going to read all that, but you can, right? There's this sort of stuff at the start talking about how Zipf was, cruelly cutting up language, right? So the man who would take roses apart to count their petals, that sort of thing, right? Destroy things. Of course, that's what we do with books. Google, of course, literally actually just cuts a spine off and scans them, so that is pretty bad. So scientists' view of language. So he goes on, and however, for those who do not flinch to see beauty murdered in good cause, Zipf's scientific exertions yielded some wonderfully unexpected results, blah, blah, blah. And then he says, actually, and this is in the introduction, he says it's really, it's nothing important because it doesn't, let me click this thing. Here it is, yeah. So Zipf was wrong. His facts were right enough, but not his explanations, blah, 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 right? And and there's this thing about Mandelbrot here. So it's a funny business. This is 957, as I said, I think. You can read this later on if you want. But point being, just a tremendous amount of upsetness and arguing and confusion. All right. I think Miller also did the thing where showed that people, and again, this may or may not be true, could remember 7 digits. If you have that story, right? That's his thing. Plus or minus 2. So he's famous for that story. All right. So as I said, Zipf didn't have an explanation that was really quantified, but Simon certainly did. So lots of other crazy things. So there's Krugman. This is the book that I first came across this stuff in, actually, Self-Organizing, but I mean, well known by many people. Talks about it for cities, blah, 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 right? Then there's this is 1999, so it's 95. This is a little piece called Deja Vu, Mr. Krugman. Urban geographers know all about this stuff. Been there, done that. And it's going to put Ijiri in. This is a Japanese guy who was involved and was introduced to geographers in 58, explanation of city size distributions, blah, blah. But then I suppose if Krugman had known about these studies, they would have been discounted because they were not written by professional economists or published in one of the 5 journals in economics. Needs to exercise some humility for his worldview. It's circumscribed by folkways that militate against recognition and acknowledgement of the struggling artisan. Sorry, you didn't say that. Urban geographers, thank heavens, are not so afflicted. So maybe at this point it seems like he thinks he's being funny. But yeah. Anyway, the good thing about the hard sciences is that in the end, someone's going to measure it again and again and again, and if you're right or wrong, that's going to be sorted out. All right. Okay, so the winner. So there is no winner, but here's one paper that shows that at least in some circumstances that random growth model that we have from Simon works out. So Sornet is sort of the big character here. He's actually chair of entrepreneurial risks at ETH Zurich. They have all these funny little departments. but he's a superstar. All right, so Zipf's law is ubiquitous. Again, this is 2008, and it's in Physical Review Letters, which is the premier physics journal in the world. So I showed this early on. These are zip distributions. This is for Linux, the Linux system produced by Debian. And it has it's named after the Toy Story characters, which is quite amusing. So so this is the packages that you get from that distribution, the number of links coming into a package from other packages. So there are a lot of them that have, that's my bad, there are a lot of them that have one link. There are a few that have up, in this case, 10,000, so it's a pretty big variation. That's probably like, an input-output kind of thing, right? You can tell me I'm wrong. What is it? Print? That's where fprint lives? Probably. So this is, so you can look across these versions and see how the package has changed, right? They're still the same package, but it's being used more and more. And so this is the number of connections at one release and then the next release. So we're going from Lenny, the latest from Etch to Lenny. Okay, there you go, Etch. And right, that terrible quick draw joke. Yeah, right. Yeah. So this is the number of this is the change. So there's a it's very messy, but there's a linear story here. This is a measure of the variance over here, but this is basic. So it's roughly you get a linear relationship between the change of links and the number of links that it has already, or inputs, if you like. So that fits in with that kind of rich gets richer model. I mean, it matches it. It's not a rich gets much richer. It's not a rich gets a little bit richer. It's actually a rich gets richer in a linear way, right? So, right, the thing should be, he who hath whatever will be proportionally given their halfness, something. But the poor do not get poorer. Okay, so that's that's one example. There are others. There's this one actually. This is going back to 2001, and it's fighting against the Barabasi-Albert stuff, which we'll come to when we talk about complex networks. So the Simon's model actually does quite well for the web. This is okay. So the web by this point is 7 years old. What is it? 8 years old. 1993 for the web. Shows that it actually does well, and we have the sort of thing you want in any kind of physical model. You have a parameter that you can go and measure. It makes a nice model, it's a nice toy model, and maybe in some cases that's it. You have a parameter you tweak, but it doesn't have any kind of, it's like the sociability of the characters in your model, which is fine. Or it's the sort of, how much they'll cooperate with each other, or something like that. It's it's a toy parameter, but this is something you can measure. This is from Alta Vista Crawls. Anyone ever heard of this thing? Okay. This is bought before Google, crushed everyone to death. Although, no, actually Google was around, so Alta Vista is still trying to live. This is 1999, so 0.1 was right, if you're looking at pages, there's a 1 in 10 chance it's a new one that you haven't seen before. So we get gamma is 1 plus 1 over 1 minus rho. That was the story that came out of Simon's model. So that's roughly 2.1, right? You put a 0.1 here. 1 over 1 minus 0.1 is, you can do this actually. 1 over 1 minus x is approximately 1 plus x. So you can sneakily do it straight away. Taylor expansion. And direct measurements of gamma at the time, 2.1 plus or minus 0.1, so that's not bad. So it turns out that, and 2.09 in another one. So that was a small paper at the time. So actual examples, they're not characterizing quite as much, right? This is a richer characterization, right? This is a very detailed characterization. So, and you can look more into it if you want to. If you have friends arguing with you, you can pull that out and go through it with them. So the nutshell for all of this is, it seems, in certain, it's not necessarily true for everything at all, but certainly this model does appear in the real world, right? You can still say that even if Mandelbrot's argument maybe gets tweaked in various different ways, you could still, this is a bit of an odd thing, you can talk about optimality being present because it fits with this particular story of optimality. So it may arise for free, which is kind of remarkable, right? So it's not, there might not be a tension between them in that sense. The reason it comes about is through just random growth. It's not because something is deciding it's not optimal and being tested against other things. Which certainly happens, say, in evolution, right? Where you get eaten by the thing that is slightly more optimal than you. Okay. Much more complicated when you get to, say, thinking about corporations and individual wealth and those sorts of things, websites. I mean, the real, these real things that we're trying to model, where, not language necessarily, but ones where things really can die out, right? I mean, languages can die out as well, but where corporations can just gone, right? So you need other more complicated mechanisms in there. The way these things kind of work, if you're in front, if you're really well in front, you will just keep accruing the wealth. So that's an interesting problem to kind of address in a simple way. I mean, we can talk about the real, right? You're opening up there's a new thing to kind of capitalize on. There's a new niche, right, that gets filled. So Google appears and becomes huge. Facebook appears and becomes huge. Right, new technology allows new companies to kind of come into being and then wipe out the ones that were kind of sleeping and so on. That's not really at all in this. It's a very interesting piece to add. So that's lying around for someone to do a really good job with, I think, rather than just talk about it like I did. Okay, of course we have lots of little citations. Yay. Okay. Love the citations. All right. Okay. Jolly good. All right, so okay, I was going to talk about this guy, Benford's law. All right, fun. So there's just a few pages on this one. It's a curious little guy, but it fits in with the whole power law story in an interesting way. Okay, got these guys. Okay, so it turns out that here's a weird thing. So you take a bunch of numbers from a text. It could be newspapers. It could be the fundamental constants of nature. Tax returns, not everything, right? I mean, if this doesn't work for a set of randomly generated numbers at all, that's not true. But there are a lot of things where this is okay. And probably the first digit, you just look at the first digit, right? So you take all your numbers, strip off the remaining digits. If it's just a 3, you take the 3. If it's a 47, you take the 4, right? And then make a histogram. And it turns out there are more 1s than 9s and more 2, right? So it actually decays as you go down through as you go up through the digit size. And it decays as 1 plus 1 over d, log of 1 plus 1 over d. And it doesn't matter what base you're in, which is a story of logarithms. Yeah. So that's a bit of a funny question, right? So I mean, there are certain kinds of sets of numbers for which this is true, and I'll show you which ones what they have to be. The thing that they have to follow for it to work. It's just odd that a number of them do this. So the fundamental constants of nature actually works, from what I understand. Numbers appearing in newspapers. It was noticed tax returns, right? I mean, just sort of. So they're hard. This if you don't know about it, it's hard to fake. You wouldn't fake it, actually. You wouldn't fake it. Humans trying to make up numbers in their tax returns, like, hee hee hee. Get this wrong. Yeah. I mean, you would just never suspect there was something that this would matter. But there's a law for the second digit, but it's much more attenuated in third digit. So around 30% of the first digits in where this works are a 1, right? Almost a third of them are 1s, compared with only so many for 9, 5%. So there's a nice little piece in here. So Simon Newcomb is attributed with finding it and wrote a paper about it. So it's not on the frequency of use of the different digits in natural numbers. And I can't remember if it was this character or this one. So Frank Benford was a physicist, rediscovered this in 38, or discovered it independently in 38. One of them found it by just looking through tables of logarithms, right? So before these funny things we used to have to actually look through it. unless you were super smart. You just know what it is. But you have to look through it. You'd have tables, right? Someone made tables. And so they noticed that the ones had been thumbed a lot more. Like the wear was uneven because it's linear. So the wear was uneven, right? So that was a curious observation. So people were coming from all sorts of reasons. Physicists are measuring numbers and so on, looking them up, and they were wearing these books out in a weird way. So this is kind of nice. So Newcomb is people usually do what I'm doing here. They say Newcomb discovered a bit we call Benford's law, and it turns out, so Benford's got it, right? And then was a little footnote, but this other guy discovered it. I mean, usually that doesn't happen, right? You don't mention the people who failed to make a story out of them. So there's Stigler's law of eponymy. I'll say eponymy. You could say eponymy. This is pretty great. This is a real thing. Waiting for the internet. Why would we be waiting for the internet? Oh, you cruel and unnatural thing. No, we did have the internet, right? Yeah. Screw you. Wow. Connecting. Your Wi-Fi is like it's through a piece of porridge. Wow. What is that sadness? Why is this sadness? Okay, so you're going to work. All right. That makes a lot of sense. Yeah. So Stigler's law of... So I mentioned Merton the other day, right? Very smart person. It's basically no scientific discovery is named after its original discoverer, right? Just as a blanket law. And Stigler attributes Merton as being the discoverer of it, and then called it his Stigler's law, so that Stigler's law was consistent. But presumably someone else discovered as well before them. So, in fact, his father was involved in some other thing here. There's the Matthew effect. We've talked about that. There's one called Boyer's law, actually. So there's even another branch that mathematical formulas and theorems are not named after their original discoverers, the dead monks that no one talks about. Yep. Should be just called, this is a 1,000-monk theorem. This is a 100,000 monk theorem.
It's just some combination of Lagrange.
And Gauss, right?
Yes.
Yeah. Like von Neumann would have discovered it if it hadn't been discovered. You could do that too. Yeah. Yeah, you could have level of brain. All right. So anyway, there's enough self-awareness of humans to have produced this. This is a good thing. Yeah? No? Okay. All right. That was on the wrong page. So let's go over here. Unable to access the internet. What a lie. Okay. So fine example of that. Good. So here are a list of utility bills. Again, that's not something you lie on. This is the one that people lie on. Death rates, street addresses, numbers in newspapers. This was actually talked about as evidence of fraud, right? In the Iranian elections in 2009, I had a student from Iran who brought this up, so it's been added to the list. These are examples. So this is the first bar is Benford's law, exactly. This proposed law. This is from numbers from newspapers, the 1990 census, and the Dow Jones Index. I think it's the closing number. What's that?
Seems like you would want to take the years out. It's not really naturally.
Yeah.
For things like the newspaper or a census.
Right.
Up until 2001 would have been.
Yeah. See, one's totally dominating. Yeah. Right. Now two's, in there. And you see some really Google Trends. I really don't have to, but Google Trends, you see that the way we talk about numbers, right? We've talked about that. That's true. We'd have to look at exactly what they took out. Yeah, because maybe they deleted the years.
About change of inflation too.
Ah.
The monthly payments.
Well, we'll see when it works. Let's see. So this is a physical constant of the universe, which is insane. Well, it's just these are the numbers, mass of the electron. Or, no, I should say like gravitational constants, that sort of thing, like, right? That sort of good stuff. G, yeah. Population of countries has this thing too, which is a bit odd. Okay, so let's see why this works. And it's a bit funny. So, all right, if it's 1 plus 1 over d, then we can rewrite that as simply just d plus 1 over d. And logarithm, the whole logarithm magic thing, right? So log of a ratio is the difference of the logs. And if we look at this, if we think about this a little bit, the numbers are then being distributed randomly in log space. Can I get rid of this? I can get rid of this, yep. All right, so if we have log of yeah, so if we have log, so this is say one, just do 1, 2, 3, I can't do logs, but 5, right? It bunches up, 6. So if our numbers, our real numbers are of whatever this distribution is, are distributed uniformly, right? Say on this little box here up to, let's say 9, then we're going to get much more between 1 and 2 than we do between 2 and 3, than we do between 3 and 4. And exactly how much we get is going to be log, whatever the base is, of 3, for example. That's the difference in this gap is, well, let's make it log 10, 2, right? That's the width of this thing. And the height's the same. It's a uniform distribution. So what do you think of that? Madness? So we can say, and it didn't really matter which base, so we can say probably of log of x, d log of x, is going to be p of x dx. And if you do d log of x here, right? So d log of x is, this is the back of the envelope, right? dx. And p of log of x we've just claimed is equal to 1. So we put these two guys together, 1, and, right, so the 1 d log of x, we just get 1 over x dx. So we get a power, so the things that follow a power law with this 1 over x works out. It's a very odd case. It's gamma is approximately 1. So that's where things explode, right? Not normalizable. But that seems to be the case. And so what you'll see is this kind of thing. These are, again, examples. So if you have a relatively uniform distribution over some period, over some range in log space, then things, there's some reason for why it cuts off here, why it cuts off here. It's going to work out. So this is the 9 gap, and this is the 1. This is where it starts with 1. I guess it's 8, actually. This is 8, yeah. Yeah, yeah. So you can see the shrinking, shrinkage. But if you had a distribution that does this, then that's just not going to work out, right? It has to be flat over a certain range.
Doesn't this make sense? Because as you have a series of numbers, the first spillover to the next order of magnitude is going to cover the entire previous range. So from 0 to the 9, it's going to be all those numbers. And then as soon as we spill over from 11 to 20, you have an extra.
You get all those guys?
The longer we spill over, the more of its magnitude, the more likely we're to stop before the end, and therefore give the earlier ranges to be more relevant.
I guess I don't think it's obvious. You have to spill over in this uniform way, right? I mean, you can be. It still has to be it has to have this uniform story. I mean, I understand it feels okay, right? But you have to have this uniform thing. I mean, so for instance, if you have numbers randomly distributed between 1 and 1,000, then it does not work, right? Because it really doesn't work. That's a uniform distribution in linear space, and the log transform of that would make it look like a mess.
But if you there was some distribution that would choose the upper range to not be specifically a multiple of 10, with a different value, then the numbers are more likely to be able to
Cluster in the lower thing because of truncation. Yeah, so that's going to work, but then you have to keep going, you have to keep going, you have to keep going. Yeah.
But just like street spaces, you're much more likely to have first and second street.
You're at the bottom of them.
Yeah.
Yeah. Yeah, I think, so there is an argument, that's true. So there is an argument for it based on mixing other distributions, and so I should include that. I think that's true. Yeah, you can get to this. I mean, this is the outcome, but you get to it from different kind of things. So maybe that's... There are funny things that happen in California, right, with the numbers of streets. It's based on the, like how far you are from the center, right? No one is from California. Like there are huge numbers. You know, you live on 10,320. Do that?
Oh,
The street numbers?
the numbers on the houses, so it's like the number of yards you are away.
Yeah, okay. Yeah. So they can be really big, right? So then you're starting to include geography, which is 2D. And Did we talk about this where Google, we did recaptures, how they're presenting the numbers? Yeah, right. Right, so the recaptures are the ones where there's a scrambled word and you have to say, so I'm a human, right? If you see two of them, one of them is encoded by the computer as a test for you, and the other one is from a book or something, right, that they've scanned. So that was all kind of okay. It's like, oh yeah, you're scanning medieval books, sure, I'll help you, that's a diphthong. Terrific, right? But then they started to put up house numbers. I mean, just they're house numbers. You see the bricks around it, it's a number on a house. And you're like, okay. I want to get into my website, and you're like, 32. Like, what did I just do? You know, like,
And always tell them to give you a different one.
you can, but it just gives you more house numbers. Then it's your own house, and then you're like, oh God. Okay, so that's a little piece in there. I could add some more for you, but you probably should add some more. Right. So, what's this bit over here? That's robustness, I think. Thing, come here, thing. System robustness, awesome. Okay, but we're going to get there. We're going to go back to some of these fundamentals here. We talked about emergence. We had all this good stuff. We had a little bit of Stephen Strogatz talking. That was the last time. And then the whole Eureka business. Gödel's theorem. Boop, boop, boop. Yeah. Why would you do that? Okay. Okay, so I want to talk a little bit more about emergence, tiny bit about self-organization, just to say what that, to define that term. And yeah, so this is a while back, 2007, but it's a very interesting piece. It's Poland, who's well loved, I guess, in Vermont. But there's a very funny, this is just an example of emergence, a very peculiar one, right? I mean, somehow from molecules we end up with this taste thing in our heads. It's not obvious when you look at the bits inside things that foods that they would at all give rise to some kind of taste. When you really drill down to it. So here's Poland's thing. Even the simplest food is a hopelessly complex thing to study, a virtual wilderness of chemical compounds, many of which exist in complex and dynamic relation to one another. And I mentioned this before, but where we are with nutrition is, here's a label on the side that tells you some of the components, right? And it's like saying, here's my friend. They have, 70% water. They have some carbon atoms in them and some molecules. They have a kidney. I don't know. It's not really great. So break the thing down into its component parts and study these one by one. We have to do that. This fits in with the whole story of science. Even if it means ignoring, you got to do it. As well as the fact the whole may be more than or just different from some of its parts. This is what we mean by reductionist science. And you shouldn't say this is bad, but I guess he kind of says this. People don't eat nutrients, they eat foods, and foods can behave very differently than the nutrients they contain. True. Diets high in fruits and vegetables. Okay, so now we're going to do this. So fair enough, you do this. That sounds good. So you find the nutrients responsible, get it out of them, and then you take, vitamins, right? and that sort of thing, or you distill it and put it into a shake or something. So beta carotene is a good example, but you can, if you just pump that in, you're going to increase cancer in certain ways. So it's really hard for us. I mean, we have to be in this state that we're in now, where we're figuring out the details, and I don't know how long this is going to take. This is thyme, for example. These are antioxidants in thyme. That's quite a lot. And what do? You break these things out and eat them, and well, we do it. It'd be great to know how this works, but in the meantime, we enjoy time and the knowledge it probably doesn't do any harm. Blah, blah, blah. It may actually do some good. And then even if it does nothing, we like the way it tastes. So, all right. This is, again, this is a great science where there's a massive gulf between theory and practice. So the baseball and bumblebees one is fluid mechanics, right? So bumblebees shouldn't be able to fly. That was the first, so a theorist says, bumblebee, they're too heavy, the wings are too small, so all the bumblebees are like, oh, you're right. So, but it turns out, and it took a long time to come, because you have to get a bumblebee, and you have to have like great little things showing you where all the air is following, moving, and then you make crazy simulations. People are doing this for butterflies. You can see that they produce funny little vortices, and it's very complicated, and they fly as they do. They fly. In baseball, right? I mean, people are good at throwing balls. Actually, I mean, people are incredibly good at throwing things. It's one of the few things that we really kill it at. I mean, humans are actually quite good at throwing. I was really taught how to throw by this massive guy who was a javelin champion for Australia when he was a kid. Just a beast of a thing. But there's a lot of all this kind of weird stuff in how you throw. And it's just very hard theoretically to get anywhere near that, right? So we didn't produce curveballs or whatever it is from theory. It's because people did crazy things, figured them out. All right, we're in this kind of mixed states in a lot of systems. Moneyball is obviously some extra piece in there where you're trying to quantify things and turn a particular game into something that's manageable, controllable. All right. It's just a good example of emergence, taste. It's a fantastic example. Self-organization. This is a term. So that could have been, way back. But it's in there. So self-organization, right? So this is where there's no centralized control. It's just a nice term that describes a lot of systems. Somehow there's again, macro phenomena, macro behavior arising or increasing complexity without that being controlled. Okay, so that's fine. You'll just hear this term. We get a little carried away. One thing we'll talk about later on is self-organized criticality, which sounds fantastic. Suck. I mean, it just sounds good. Those words are really powerful. The criticality is we have a sense of criticality, a common sense, a common usage version of it. But this is actually a very special physics version we'll come to. But of course, then it comes back out to the general public and sounds great. All right, so lots of decentralized processes give rise to emergent phenomena. I mean, fluids, right? And that's a good example. Gas, liquid, solids, these guys like each other in some ways, molecules and atoms. Magnetization is something that emerges out of spins. Hopefully I'll show you a little example of that. People, imitation, people and animals, lots of things happen through imitation. And then, there's a broader question here, and we'll come back to it. We'll touch on it now. Complexification, right? We're rising out of nothingness with this constant complexification over a long period of time. It could all explode. We could, be like dinosaurs who smoked too much or something, whatever they did wrong. It's a Gary Larson joke. Never heard of him, right? This is a really great question. But it does seem to come out fairly easily, given we're supposed to turn into soup. Again, physicists. So the upshot of all of this is that these things are not complexity and emergence, very powerful framings, but they're not exactly defined. There's no general theory of complex systems. There are many theories. But there are some very general approaches to kinds of systems that are similar, and we've when we talk about networks, we'll see this. We've seen it with the rich gets richer model. These are things that approximately appear in lots of different places. So people will get confused about that. They'll talk about theory, right? They'll talk about complex systems theory. There isn't just a theory of complex systems. There are many different theories. But the problems are absolutely universal. They're really there. So we're moving into understanding systems, and some of these systems, maybe it's better just to count up everything and use some sort of inference from thing, right? Some sort of crazy machine learning thing that does it. And that's what some of the big, Facebook and Google and those guys, that's what they're doing, right? That seems to work, right? You don't necessarily have to have a beautiful theory for it. You just have an approach, an algorithm that contends with it. We'll use whatever tools we need to solve all this, and that's part of what this course is about. You'll see lots of different things. This is my little joke. Reality is theoretically weak, and science is describe plus explain. So these are, we're in a good game right now. We're emerging out of reductionism. We still have to do that, but we're building systems, understanding systems, and we can do it. This is totally fun. Here's a really good example of how to do science, which I have in here. And I want to show you some of this interview. I think it's only a few minutes. So cat lapping, right? So this guy, so there's a couple of guys at MIT published a paper in Science on the lapping of cats, right? And it's because one of them was watching his cat one morning thinking, that's kind of interesting. So, I'll show you this. It's fun. This is a reasonable thing to do today. Oh yeah, right. So you hate me.
They do it for various viscosities of liquids.
They do it for different size organisms, which is kind of interesting. And I think they used a...
Before Mike could see his banking and investing on one page, he opened a Merrill Edge investment account and linked it to his Bank of America bank account to help free up plenty of time for the here and now.
Right, they got YouTube
That's Merrill
videos
Edge
of bigger
and Bank of
cats
America.
to look at their rate, because it's a function of size. But the viscosity is a very interesting question. I don't know. We'll see.
We've all seen domestic cats lap up milk or water, but few of us have probably thought about how our furry friends manage to draw water into their mouths using only the tips of their tongues. In a study published this week in Science, Roman Stalker and Pedro Rees from MIT and colleagues use high-speed imaging to reveal the physics of cat lapping. So Dr. Stalker and Dr. Rees, what prompted you to study the physics of cat lapping? Some people might find this to be an unusual topic to study.
I certainly agree with you that it is somewhat unusual. What prompted this study on cats was, in fact, my cat. I was watching him one morning of 3 years ago over breakfast as he was lapping his water. And it occurred to me that there was an exciting biomechanics problem hidden behind the commonplace and apparently simple action of lapping. The cat had to somehow overcome gravity to get liquid from the bowl into his mouth. But how?
And as Roman said, this project was unusual in many aspects, starting from the topic. However, we attacked it, as we often do in our research, by a combination of detailed observations, systematic experimentation, and mathematical modeling. So this project can therefore be really seen as a blueprint of scientific research, which often starts by posing a previously unasked question. And also, our work shows that there is a wide range of physical processes out there, from nature and in technology, even in our everyday experiences, that way to be studied and explained, and it is very exciting to pursue this.
In your experiment, you used high-speed imaging to capture the motion of both the cat's tongue and liquid during lapping, and mimicked this action in the lab using glass discs. What did you find?
Well, so if you move to a cat lab, you immediately realize that the process is too fast to be captured by the naked eye. In fact, a cat's tongue reaches an incredible speed of nearly 1 meter per second. And this is why we had to resort to high-speed imaging, often used in science to slow down action that's too fast to be seen otherwise. And so our videos show that the cat's tongue extends out from the mouth and down towards the liquid bath in the form of a capital J, such that the tip of the top surface of the tongue is actually the only part that touches the liquid. The cat then very rapidly draws the tongue back up, and as a result, there's a liquid column that forms and extends by inertia. And then when the cat closes its jaw, it drinks a portion of this column before gravity breaks it up. Now, what is remarkable is that cats seem to know about this balance and lap at a frequency that maximizes this volume ingested. Now, every cat owner knows that you can't force cats to do pretty much anything, let alone force their lapping speed. But we needed to do precisely this to test our theory. So to get around this, we developed a robotic mechanic version of the cat's tongue with a glass disc that moves upwards. And with this, we then had full control of the process, and we could study the fate of this liquid column for different lapping speeds. So these careful model experiments were really crucial in helping us understand how lapping depends on the competition between inertial forces and gravity.
And finally, do your findings apply to all felines or just domestic cats?
Our findings suggest that the lapping mechanism that Pedro has just described should apply to all felines. The physical experiments with the glass discs prompted us to develop a mathematical theory that predicts how the lapping frequency changes with feline mass. And in particular, we predicted that larger felines should lap more slowly. To test this prediction, we used two approaches. First, we went to the Zoo New England in the Boston area, where we were fortunate to strike up a collaboration with mammal curator John Piazza and his team. They gave us access to filming large cats as they drank, including tigers, ocelots, lions, and jaguars. We then realized that additional data were readily available to us in the form of existing YouTube videos that people had posted online after having been on safari to Africa, for example, or having had bobcats roaming their backyard. From all of these videos, we extracted the lapping frequency of different felines, and we found that as our model predicted, the lapping frequency decreases with increasing animal mass by the same amount that we had predicted.
Thank you for your time, Dr. Stocker and Dr. Rees. This interview was produced by the Office of Public Programs at AAAS, a nonprofit science society that publishes the journal Science.
So it's clearly kind of ridiculous, but you can do this in fluid mechanics because we have equations, right? So there's a start there. So you have theory. This should be this may sound absolutely obvious, but it's not. It's absolutely forgotten all the time. Experiments and real reality, right? And as I recall, I think they used some sort of robot that was developed for the space station. Right? They co-opted it to do this thing. So you need these guys all matching up with each other. And a lot of fields, there's a huge gap between these two places, right? You can't measure this stuff. You can't even do these things. So there's a huge abundance of theory, right? Physics has been like this for sure, for thousands of years. We've had a lot of that sort of stuff. But then things close down, right? No one's going to argue about atoms anymore. Or no one's going to come up and say phlogiston is real, right? It's done. But we are, and then there's a great question of how far everything goes. I mean, with studies of people, how much do we, big scale, large scale social phenomena, what do we get to? Even say, the power grid, right? And how far do we get with that? Because we seem to have created something we can't quite describe very well. We really have trouble describing it, which is amazing, And our theory is actually really limited. It's really hard there. I mean, we know about electricity, right? But it's still very hard to model that. So that's, there's a limit, and science, of course, is able to show its limits. I mean, like weather prediction, we can quantify how the limits we can get to. But it's always good to kind of know where you are in this space. And anyway, this is a perfect example. And fluid mechanics can do this sort of thing. Maybe this means it's jumped the shark, but it's pretty cool. So dogs don't do this. Dogs just kind of just like bash water up in the air. Different thing. I guess I'm running. Well, let's see. Maybe I start on StatMech in the next piece. Science published it. There you go. All right. So modeling, we've done a little bit so far with really just describing, which is the power law stuff. We've done some describing, done some modeling with the rich gets richer stuff, which is nice theory. Obviously measuring real things there as well. So This is usually hopeless, right? Emergent behavior from many interacting agents, very hard. I mean, we do have some very, very large scale things now for, say, fluids again, but they're still small physical spaces. So lots of computer-based models. And dynamical systems is the great kind of field for understanding these things, phase transitions and all sorts of this kind of behavior. Cellular automata has been a big area of study, I mean, largely in some ways because we could do it, right? We could simulate all these things. So we repeatedly make mistakes where we try to model all of human behavior with any of these things we've become quite good at. Everything is now a network. Not true, right? And we like power law distribution, so everything has a power law distribution, right? So we have to be a little careful with what we're doing. All right, so just so you know, right? Lots of different techniques. There's the whole realm of differential equations, all these sorts of things. You need good statistical techniques. These things keep being developed because data gets bigger and bigger. This is not something that's just done. Stat Mech, computer science, lots of things coming over from there, lots of modeling. And I've said these things, but one of the big advances, and we'll come to it when we talk about networks again, is just the simple observation that these interaction patterns are, of course, networks, and that people know this, they knew this, but they didn't talk about it in this way or study things in this way because we couldn't really actually quantify it. So much more about that later. All right, that's just simple things that should make sense. So let's get on to stat mech. So very often what passes for complexity science today is something, this is not entirely true. The main themes in complexity theory have been studied for more than 100 years by physicists who evolved a toolkit of concepts to which complexity studies have barely added a handful. This is a little rough. This is written in 2003 or 4. But we do have this great body of work, stat mech, statistical mechanics, exactly what it is, mechanics that's probabilistic or statistical, and it's a science of collective behavior. So that kind of thinking, of course it was for gas particles and other things, is a very good grounding for moving up to all sorts of other areas. So basic game, right? We have simple rules for how things interact at a small scale level, and they give rise to collective phenomena. And often it's a game type situation where we're trying to put in just a few little pieces, like the rich gets richer model. Innovation rate, very simple, very easy to understand, gives rise to something that's surprising. So I'll talk a little bit about stat mech. We'll see how maybe this is it for today, and then that'll lead us into studying robustness. So can you read these things? All right, so these are up and down spins on a 1D lattice, right? So that we think about magnetic systems. Here they're on a 2D lattice, and they're interacting with each other. Obviously this looks better on a real screen. This is 800 by 600, I think. It's pretty bad. This is, so there's crazy, it says happy and sad here, right? So people start to do crazy things like, I'm right wing or left wing. Let's put that on a lattice and make humans, that's a bit silly. This is just for magnets at this point. It's already a very silly model for magnets. Right? It's kind of amazing that this works, but it does. It's kind of an incredible achievement. So this is the so-called Ising model, and it comes from the 30s, if I've got that right. I was a graduate student, made up this crazy model. So it's already a toy model for these things. So very simple, up and down spins, that's it. You put them on some kind of lattice, so then there's a huge enterprise in studying all sorts of lattices, right? Hexagonal ones in 3D. If you have them by themselves, then spins they like to align with each other. Temperature tends to break up those alignments, right? So increasing heat makes you increase the temperature and the fluctuations go up. It's a Drosophila of stat mech. This is sort of the basic thing, right? And so here's an example for the 2D system. This is the overall magnetic field. This is temperature. So as you cool the thing down, what you start to see is at some critical temperature, this is the emblematic phase transition, you start to see the spins align in one direction, all right? And there's a little randomness as to which way that works. And it could be up or down if you've got, this is basically like a big waffle, right? Waffle. Okay, and at 0 temperature, they're all pointing in one direction because they like to align with each other, but the temperature is so low it's not forcing them out of that alignment. The models are usually pretty simple. It's just nearest neighbor effects. You can talk about effects with other ones, but these will be just the 4 local ones. And you actually, okay, so here's this word criticality. These are the interesting points in these systems, right? So once we're above critical temperature, it looks kind of the same. We're moving around here, there's nothing too abrupt. But here's a big transition, right? Suddenly there's a macroscopic magnetism. And it could be either way, but as you cool it down, it goes boom. And this can be very sharp. It depends, there'll be theoretically you figure out what the derivative is like here. It might be something that's finite, or it might be an infinite jump, right? Or it could be that you have a system where you actually have jumps, right? So that's a so-called discontinuous phase transition. Right? These are, if you like, first order or continuous, different things, but it's it's discontinuous in the derivative, but it's a continuous phase transition. So there isn't a huge shock, but that transition is pretty rapid, and macroscopically things have changed. So we talk about this as being the critical point. This T sub C, it's a critical point. And that's fair enough for these systems, right? And we have this word criticality. Then we go back out to talking about social systems or whatever we're talking about. That word gets a little, let's see if this one still works for me. Wow. I don't really trust you. Okay, so, but it seemed to go. Okay, so here's temperature. There's a critical temperature here. We're going to start. It's warm. And okay. The color palette is Slytherin. So if we have a nice high temperature, okay, then it's going to, is this going to? Yeah. Okay, so let's put the temperature right up. Boom. Should be a nice big mess. Right, so this is a 2D case where they're just looking at each other. And then if you cool it right down, they start to join. So you can see the lure of this. Like this could be opinions of your friends or whatever it is. You can see the lure of pulling this out to social phenomena. It's already a ridiculous toy model for magnets that works amazingly well. It captures this whole feature of spontaneous magnetization and so on. So these guys are fighting for each other. Now we have these boundaries. So anything that's a little island is going to get chomped up because there are more on the outside, right? There's roundedness. They're all going to flip at some point and will disappear. So it'll take a while, but there's going to be, and it's going to be wraparound boundary conditions. Maybe it's not actually. Oh yeah, you can't see the bottom. So, which means we're on a torus, right? So this is a magnet on a bagel. You can use donut if you want. But this is, right, macroscopic behavior. Locally, they're just interacting with each other. This is totally good fun. Let's see, let's do, right. And so then there's an external magnetic field, which you put on top, and you can bias things, right? So this is going to drive them in a whichever way they're pointing. So that's just going to wipe it all out. Right? But if you get above the critical temperature, it's all going to fluctuate again, even though there's an external field. So that's a whole other fun thing to solve. But the external magnetic field, this is like, you can imagine this. This is, whether the place is right wing or left wing. Lots of craziness. But it's a beautiful example. So there's a whole other field area called percolation, which I'll talk about, and I think that would be a great problem for you guys to work on. Percolation is kind of related to this, but very, very simple idea. So you just have a grid, for example, or all sorts of lattice problems, and you simply, with probability P, fill in each square, right? Let's do that. Okay, this is percolation. The idea is, if there's enough connection, then, and you imagine this is emptiness, then water might flow from one end to the other. So it percolates through the system. So there's a big deal for getting oil out of the ground, for all sorts of other types of problems, but it turns out to have a very beautiful kind of, for stat mech, it's a great example, right? It's not necessarily, you don't necessarily have physics or like temperature involved. You really just have a probability story here. Lots of things can be solved with that. and you know, we aren't going to, we can't, I mean, it's a whole course, right? This thing is several courses, but I just want to touch on a little bit. We'll certainly have it in networks. It's beautiful in networks. You can imagine the same thing played out on networks, right? Where nodes are in and out of the game, depending on the probability. But we'll build that up. Okay, so that's just a tiny introduction to stat mech and the idea of criticality. And so you'll know that when people start talking about that it's a little bit of a weird thing. Ooh, they got tranced. Okay, so I think we're good. We're good. Okay, so we're going to start talking about robustness on Thursday, and that is, you know, again, really, really interesting, good stuff. Okay. 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 So office hours tomorrow. Come to office hours. We'll talk about things. Lots of fun. Turn these things off.